medical system design and development. So what I'm going to do in next 45 to 50 minutes, I will try to give you glimpse of what is the imaging subsystems across and how does it work in very high level. I'm not going to explain the imaging techniques because that is a wide topic and probably not possible to cover into that. And then little bit I will touch upon that how X-ray is generated and how the electrical engineering and power electronics is important in entire things. Okay, but anywhere you can stop me if there is a questions and I can take it. So let me know if you all can see my screen.
Yeah, it's visible, sir. It's visible, sir.
Okay, so a little bit in addition to the, this is what I am, mostly it is covered. So I have worked mainly into the, I will say optimization into the X-ray source for the last so many years. And you can little bit get to know about my personal family, my hobbies and other things. Okay, so I'm a very extrovert person. I love traveling, cooking, and most of the experience, as you told you, is into the X-ray generation. 17 plus years into the G healthcare and 2+ years in Scanray, and then some portion to Crompton Greaves. I'm a certified DFSS and the reliability person too, which is very important into medical system. You know, medical system is all about reliability because it's just not electronic circuit. It's just electronic circuit which is used into scanning the human, and sometimes if it fails, it can take that life of the human. So reliability is very important portion. So that's why I'm a certified reliability practitioner, and that's what I have been doing. Okay, so moving to the imaging system, you know, so how many, I'm sure that you all must be knowing about the CT. Okay, so CT is like it's not as computed tomography. Plus, will it be interactive? Means people will talk, or it is just one-sided? Just want to know.
No, no, the participants may ask the question, and as per the convenience of yours and participants, but it is open from our side, sir.
Okay.
Participants may definitely interact with you.
Okay. Okay. So, you know, tomography, if anybody knows, tomography is a kind of techniques where we try to image the inside. So suppose if you take a orange, then what happens that you slice the orange, so you will get the structure, and then we stitch the slices, you will know that how the inside structure of the orange is there. So the only difference is that here we have to slice the human body, but you cannot physically cut the human body, right? So, but the principle remains same. We have to slice the human body and through the X-ray, and then stitch together to see that how the image looks like. So that's why it is called computed tomography, because we are using X-ray, and then there's a huge calculation behind that on the imaging side, that where we stitch the image together to really see that. So if you can see in the picture that there is a patient table where patient will lie. If anyone has gone to the CT scan, I'm sure you can relate to that. And then the table moves and takes you through the board, what you can see here. And then although it looks fixed, but inside there is a moving structure which is called gantry, and on the gantry there is X-ray source and detection, which you can see on the bottom picture. So that's how we take. And if you see that the imaging technique, there are three types of, there are many types, but to understand it, that One is axial, where your body is fixed, means table is fixed, and then gantry rotates, and then you will get that some picture of that, of one slice, that is called axial. Then your gantry is fixed, then the table moves, so it's like slicing through the length of the body, right? That is called longitudinal. And there is another type of scan where full body scan happens, where it goes into spiral, means table moves and gantry moves. So you can understand that it is kind of a spring movement, right? Spiral movement. So uh, that is this kind of things. But whole idea is that, sorry, whole idea is that we have to go and slice the body and then stitch the image together, and then you can see. So that's what you see, that couple of pictures I have added here, that if we have to take your lung, that's what you see, the top pictures, or you see the middle picture where we have done the slicing through the length of the body. And so whole idea is that once we slice, we can see the internal structure. And then since it is computer tomography, so you can do a lot of post processing to see that. Only if you see the top picture, that if you want to see the lung, I can hide other things, I can visualize the lung. If I want to see the bone, we can suppress the other image. So it's all possible. And then you can see that this beautiful image of spine, once we have all the slices, we can stitch together to really see that how your spine looks like, or how your other internal body looks like. Okay. There are something called contrast, which you see on the bottom. So what we do here is that we inject the iodine in the body, okay, through the oral or through the some other media. And then what happens, that iodine goes and interacts with some kind of tissue, or tissue which is cancerous or other things, and then it gets bright picture. So you will see that there are sometimes people will do the normal CT scan, or sometimes people will do the contrast CT scan. Okay, so these are the various techniques used, but whole idea of the is there that there is X-ray source, and the X-ray source is used to slice the body and take the slice picture, and then each slice is stitched together to understand that what kind of problem we have in different parts of body. Okay, so another CT is called PET CT, where it's actually the CT, but normally when you have a cancerous cell, it's very hard to detect. So what we do is that there is some element called progesterone, which is highly emittive. We inject that progesterone into the body, and then the imaging is done. And on the top of that, normal CT imaging is done. So you can see that this is how the PET image on the left side will look like. And then once we take the CT slice and see, really locate that at which location that particular cancerous cell or tumor is there. Okay, so these techniques also comes under the CT, but the idea is that in place of iodine, we inject the progesterone, and there is a different detector which takes the radiation. This itself is a emission, radioactive element kind of things. Okay, so and then we take the normal X-ray imaging, we superimpose, and when we do that, you can stop me if you have any questions anywhere. Okay, I'm sure that in India, cath lab is very famous because we have so many patients of the cardiac arrest. Okay, so this machine again is called all the heart related things. Okay, we do scanning. For example, we inject and then take that, how, where is your blockage and where is this one. We do stenting. So this is a machine which is used inside that operation theater, where we do all kind of operation on the heart. And you can see the image. This is how we inject, and we take the picture, that you can see really all the veins where the contrast is going, you will see the black, and if it is not going, you will see there. So you will find that where is the blockage is there, so that it can be identified for treatment, either stenting or bypass or whatever is there. You must have heard the name of the this machine, which is very famous, is C-arm, typically used into the orthopedics operation theater. Okay, so your first we see we can, this is a mobile thing, so we can take into the emergency ward, we can take to the room wherever patient comes, and we can take into the operation theater also. So this is widely used into the trauma room where accidents or something has come. Then we will see that what bone is broken, where is the problem, what has to be fixed. Based on the imaging, then the doctors plans the operation. Then you can see that many mechanical parts inside, right? So this is also used into the operation theater, where exactly where we have to do screwing, we have to put some metal supports, those kind of things, so that you don't touch the nerve but you can fix the bone. And this is very handy machine, but again it's x-ray based, so that we can use through the operation of after operation for the monitoring purpose in trauma room. This is very interesting machine. I'm not sure if many knows about that. This is called bone densitometry. So here X-ray is not into the direct imaging, but what we do that we produce X-ray and then we put some kind of filter to differentiate between the low intensity X-ray and high energy X-ray, low energy and high X-ray. And dual energy X-ray is used to understand that pattern of your bone density. So we actually count the photon of the how many low energy photon has passed and how many high energy photon has passed, and based on that there is a database. So we predict that for that particular bone what is the density, okay, and how it is degrading, especially for women once they cross 40 45. This is a big problem in women because of the various reason, the way their lifestyles are there, and bone tend to be very porous over a period of time. So this is kind of a diagnostic equipment where there is no direct imaging, but it's based on the photon count. And for that purpose here, if I can say that the most stable X-ray need is in this machine where it is used. And you can get the scan, and then you go after 6 months, take the scan again, and go after 6 months, take the scan again. So if the bone density is varying, that means you have a shortage of many things, and you can take the particular action based on the root cause of the problem. uh, So moving to the nuclear medicine, as the name says, it is a machine which has two types of imaging. Okay, so what typically I will tell you 1 minute here too. So when you need a very advanced diagnosis of, for example, a brain tumor which is hidden behind the big bones, and it is very difficult uh, to to detect through the normal CT and other things, then we go for nuclear. Here, what we do that we inject a highly radioactive material in your body, and then what happens that radioactive material through the blood, it reaches to the brain, and then wherever brain or any part of the body, and then it interacts with the cancerous cell, and it starts illuminating, and that is captured by the characteristic of that is matches with the gamma. So there is you can see the big tube camera, it's called gamma camera, which detects the radiation illumination, but it does not have any reference to the bone. So in this we have another parallel kind of CT which takes the bony picture, and then you merge. You can see here. So we took the bony picture of the body, and then we locate where is this illumination is coming. And once that illumination, then you can see that okay, in this area there is a hidden cancerous tumor, and then that is planted. So this is kind of advanced cancer detection equipment. In India, you can find in some big hospitals, rarely found because it's very costly equipment. But it happens to be my first project into my career in 2002, so very close to mine. But I don't see many system in India, but a very very powerful equipment to detect any cancer early. And then this field, I think most of you are aware. I am sure that one or other time you have gone to the X-ray room or mobile system. So this is typical X-ray machine where you take the 2D image and sometimes 3D image for your chest, for your skull, for your lumbar. Any problem comes, you can see that, right? And this is pneumonia, typically right now very famous imaging happening for the COVID situation, where we try to take the X-ray of lung and see the status of lung. Okay, and so any questions on the imaging systems? Anybody?
Participants, you may ask the questions if you have some queries on this particular imaging systems.
Okay,
Sir,
so
I have.
yeah, go ahead.
Sir, actually, in the nuclear, in the recent slide, you said we injected a highly radiation material. Then will this not
Radioactive
impact
material.
the other parts?
Yes, that is very good question. So if you see that any injection, iodine, positron, or this highly radioactive material, isotopes, there are a lot of side effects and lot of test is used before injecting. But it is in medical industry, it is always like a benefit versus loss, because the X-ray itself is harmful to the body. So that's why I told you this is done to really when the patients are sick and the kind of we know that where is the already patients are suffering from cancer. So now normally what we do here is that we detect the cancer, and then if radiation therapy has to happen, we know that exact location of the cancer so that we can point the radiation therapy. But this has a lot of side effect, yes, a lot and lot, but it's always like a benefit of killing the tumor versus the side effect. So always that's the way this technology is used. Does it answers your question?
Yes, sir. Actually, my net is connected.
Yeah.
Actually, I have one query, sir, actually from you.
Yeah.
The intensity of the nuclear radiation, sir, which passes to the human body. So,
Yeah.
like, is there any fixed kilogram of the radiation that we pass, or how you decide actually how much amount of intensity of radiation should be passed onto the body?
Yes, actually there is a big standard of that how much we should give depending on the for this scanning. Okay.
Okay.
So normally if you see that this kind of radiation is measured into the Curie or gray kind of
Yeah,
things.
kilograys. Yeah.
Yeah. So it should be less than 2. Okay, that is kind of there can be a side effect, but it will be less. Okay, means less harmful. It does not burn. See, radiation will more than this, no, can directly burn or something and harm your other parts. So this is kind of can cause some side effect, but safe limit. So those kind of things is taken care while injecting. And but if the cancerous tumor is very much inside the between the thick bones, then we have to give a little bit more, because it has to, this has very less half life, this kind of radiation. So it is very quick, you give and then it start decaying. So little bit more is given, because from the injection point to that particular things. So there are a lot of techniques here, which doctors decide before giving to that. But yes, there we try to give always. There is that as low as possible. That is
Yeah.
the term. Yeah.
Sir, one more question.
Yeah.
Sir, actually, while projecting X-rays on our body, we can only see our bones only. Then what about the veins and other things?
No, we can see everything. Uh, I will say, but what happens that if you go to the CT, okay, so what happens, no? Uh, let me tell you. Sorry, one. So, if are you able to see my cursor?
Yes.
Yeah. So if you see that I took one slice, okay, in this now I want to see only bones. So I actually suppress that soft tissue, this one, so I can see the bones of this one. This is actually a slice of where the lung is there. It's kind of middle of your chest. You can imagine. Now, if my interest is to see the lung, I suppress the bone. So you see that white, I suppress the bone and I can see only lung. And then if I have to see something in between, neither lung or not bone, in between something. So those kind of things. So, but yes, what you are telling, that typically what is known outside is that X-ray is used to picturize the bone. That is based on the normal this one. But X-ray can take picture of other things. Only thing is that to differentiate, it has to be control and different energy band. Okay. X-ray is also used to scan the non-medical things, right? Like PCBs, parts, metals, and other things. So it is easy, but when it comes to, and then there's something called bottom picture. You can see when we are not able to distinguish, then we put contrast. So that soft tissue, wherever the contrast iodine is going, no, those areas coming, and we can see that. Okay. So there are many techniques with contrast. You can see lot of soft tissues. Normally also we see, for example, if you see that normal, this is the normal X-ray picture, right? Do you see my this one? So you see that there is a chest bone which I can clearly see. Okay. But you will also see that there is a heart, there is a lung, and then bottom there is a kidney. Okay. Everything you can see. Only thing that you will not be able to see very clearly, because here we have not controlled, it is one sort. But if I go to CT, and that's where we model it, I can focus on this area and I can get imaging of that. If you want further enhance imaging, then I can put contrast and other things to differentiate between two parts. So what happens that, why bone? Because bone and muscle has totally different properties. But when you go into the soft tissue, the difference between cancerous or effective part to this, the properties does not change much. Okay. And that's why people say that X-ray is good for bones and for others it is not good, but we can image. Hello.
Yeah, sir. Thank you.
Yeah. Okay, any further questions on the imaging system? Okay, if there is no, then whole important things what we saw, that all system needs X-ray generation, right? And that is my second portion of the presentation today. So how we can generate the X-ray? I'm sure some of you may be aware, and some of you. So how many of you know that who is father of X-ray? It's Ranjan.
No,
Yeah.
no.
Uh, yes. So this is actually X-ray. X-ray was invented by an accident. Okay. So and Ranjan, mm, that's why the X-rays unit also comes into the Ranjan. So actually, he was doing some experiment in a tube. Actually, he was discharging the high voltage. Okay. And there was some kind of black screen was kept nearby, not intentionally. So it was a illuminating screen. So what he saw, that whenever he was doing some phenomena in the vacuum tube, some kind of shadow was appearing on the screen. Okay. And that's how he started thinking, oh, what's happening. So it was not at all X-ray experiment. It was some kind of experiment on the high voltage, how we can discharge the high voltage through the vacuum tubes. So that's how it started, and that's why he is called the father of X-ray, just for the knowledge to, if you don't know. So before I go and talk about this one, so what happens is that to generate the X-ray later, you can see topics that it's called X-ray tube. So normally there are two types of X-ray generation known, and what happens that if a accelerating electron goes and hits an atom, okay, two types of things happens. One is that it goes and hits another electron and ejects both electron together, means one which is going in and other which was inside the cell. So the moment it goes and displaces the inside electron, there is a vacancy of electron, right? For the stability, so then atom becomes unstable. So the electrons into the outer shell jumps to the inner cell, so you all know that from the physics, the outer cell has most energy, and when it jumps to the inside cell, there are energy release, because energy can, the conservation of constant energy. So through that, there is energy release, and we found that a portion of energy is in the form of the X-ray. Okay, and then some goes into the heat, and a portion of, a very small portion of it, this one comes as a X-ray. So that is called characteristic X-ray. Okay, this phenomena. There are other types of X-ray where what happens, it does not hit the electron, so it goes really to the positively charged, so it is slowing down, so electron was at high speed, and then it is approaching, and then it is kind of going towards the positive, and then inside there is acceleration, and then goes out. So during this process, what happens that you have loss of energy from the electron, and that energy uh, kind of is converted into two types again, heat and then the X-ray. So if you see the graph here, you kind of give the energy, which is kV. Okay, and then once it goes into the atom, then you can see that there will be some kind of radiation always will come, which is called breaking radiation. That is continuous, and then we have a characteristic, because at particular kV, the first phenomena happens where electron can displace, and that depends on the types of material is there, what is the target material, right? So in medical, actually we don't differentiate much. We can do imaging based on both type of radiation, but typically we characterize the X-ray tube in such a way that it works in this range where the peaks come. So characteristic X-ray is used, but there's no only why we use here, because amount of X-ray uh, generation in characteristic kind of phenomena is high, and also it has a kind of very stable energy or characteristic, you can say. We can define the X-ray in this region much better, and later you will understand that we need the X-ray control, right? Which means that we need the X-ray energy control. Okay, and we need the quantity of X-ray. So typically we use this one, but theoretically we use, and there are some types of target material and transmission type where we are using the breaking radiation, but normally widely used is the X-ray characteristic X-ray in the X-ray tube. Okay, so all the systems what you saw, there is a power architecture around this. Okay, so now by this time you all know that X-ray is generated from X-ray tube. Then we have a patient, okay, and then the X-ray passes through the body and falls on the scintillator. A scintillator is a surface where it illuminates based on the radiation, right? So it actually converts a negative, if you all know that our camera, negative image. And then based on this image, there is a detector or film, and then we process the image if it is high-end system. For example, in typical X-ray, we stop here, but in image CT or other things, we will go to the imaging process. And then, but before that, you have a powered PDU power distribution unit, which takes the power from the mains or from the any other source, and then gives to the X-ray generator. X-ray generator, why it is called, although the X-ray is generated with tube, because tubes cannot generate X-ray on its own. Okay, so you need certain types of activation power supplies to generate the X-ray, and that's why this is a power supply unit, as you can see in the picture, which is called X-ray generator. So anytime when you hear that X-ray generator, it is not the tube, it is actually a set of power supply which helps that's how the industry has adopted. So you can always debate, but that's how. So when we say X-ray generator, it is not the X-ray tube. Okay. It is a set of electronics and other electrical system which helps X-ray tube to generate X-ray. Okay, and then on the top you have a interface system where you, in simple, it will be system interface like console, control unit, data acquisition, image display, depending on the many things which connects everything. So this is a very simple architecture you can imagine for any things what you saw earlier, any machine. So here we go to the X-ray generation. So you have two types of. First of all, you have to understand a couple of things. I'm sure that every one of you know that the bulb, right? Our normal filament bulb, you know. So can anyone answer that? What is the gas filled inside the bulb?
Neon or
Anyone?
argon.
Argon,
Argon.
yes. Yeah. So you know why argon? Because this is called the inert gas. So what happens when we heat the filament? Lot of heat is generated and electron clouds comes around this. Okay. Then if you have something like a sorry, my. So if you have something like a different gas, it will start catching fire, right? So what happens that we give something kind of a gas which is very resistive to the any kind of this kind of phenomena, so that filaments keep glowing and you see the light, and then only heat comes and light comes and you see that. In X-ray, as I taught, you need the electron. Okay, you need the electron, and then the electron needs to travel from filament, which is also called cathode, to the target, which is called anode. Okay, so there is two phenomena has to happen. One, to emit the electron, it has to be heated like a bulb, right? Now we need to have either an inert gas or something, so that when we heat filament, we don't create anything, this one. But second phenomena is that if there is any gaseous things, gas has molecules, so the electron cannot move freely, right? Which means that then that this has to be gas free, and that's why we tell that X-ray tube or this insert has to be uh, vacuum to a level where more than 99% of electron can travel from cathode to this one freely. Okay, So, and the moment it is vacuum, the remaining 1% gas also has to be into the inert form. We cannot have 1% oxygen, or we cannot have 1% as some kind of moisture or other things, right? So whenever we make a X-ray tube, we ensure that first we process so that all the this kind of gas which can create problem is removed, and second, we remove the gas to such a level that it is almost near vacuum situation. Okay, and the reason is that the electron has to move freely, right? And once it is generated. Okay, and so you can understand that. So what we will need is that we need something to make filament on, and we need some power supply to which will ensure that electron moves from cathode to uh, anode. So how we can do that? Anybody can answer?
By applying very high voltage.
By applying, yes. So that's why you need very high voltage, because even if you give a small, it will move, but depending on the voltage you apply, the I talked about that energy, right? The energy will be lower. Okay, so when we apply higher voltage, higher energy is absorbed by the electron, and it will hit the target with the higher energy. Okay, once it hits the target, so typically in medical application, based on the characteristic what you saw, we apply around 40 to 150 kV. So the lower kV we use for the soft tissue, and higher kV means more we use for the bone tissues, bony kind of things, right? So suppose in mammography, where our X-ray is for typically on the soft, right? We do the women's chest for the any breast cancer, or this kind of things. So in the breast cancer, there's no bone, so we will be into the 40 kV range max to diagnose that breast cancer. However, if you go to the normal X-ray, we go to 120 kV and 140 kV for your thick bones, so that it can penetrate. So we need around 40 to 150 kV, okay, which is used, and then it goes and hits a target, which you can see. So what we discussed, that once it hits the target, 99% of the energy goes into the heat, either it is characteristic X-ray or breaking X-ray. So more than 99% of energy converts into the heat, and less than 1% converts into the electromagnetic radiation. And in that even if we have tuned and other things, maybe less than 0.8 or 0.5% is the X-ray. That's how it goes. So, and that will go through all, it will go through the X-ray, right? And then what we do is that you cannot generate X-ray all, so we do the shielding of the X-ray. Okay, so that's where we put the heavy metals, something like lead, which absorbs, and only we open on the window which is intended to go towards the body of the patient. Okay, so this is what you can see a typical X-ray. In typical X-ray, you need two power supply, high voltage, you need X-ray tube, you need high voltage, you need filament, right? Now the real challenge comes. This has a limitation. How whatever metal you add, and if some of you from the mechanical and thermal background, the target where the electron is hitting is a pointed things, right? We cannot hit all over that. For example, if you know the basics of the optics, to have a sharp image, you need point source of the light, right? For example, our projector, if you are using, has a very pointed source of the light, so that you get every letter and other things good on the screen. Suppose if you have a big light source, what will happen? You will have multiple very hazy picture. You will not be able to understand that what is the edge and other things, right? In X-ray imaging is exactly the same. So the heating area has to be as small as possible. Okay, so that X-ray looks like it's coming from a point source, and the moment it is point source, your image quality of the anything will be much better. So So the area where it is hitting the electron is called focal spot, and the focal spot size has to be as small as possible. For the better imaging, you need to have as high as X-ray, right? Or as fast as X-ray. So you see that contradiction, which means that I will produce more and more heat in smaller and smaller area. So then what will happen that although this will never get, but point things will get burned and melted very soon, right? So to avoid that problem, you can see on the right side, then we start that this target we start moving, okay, and moving at a very high speed. So the moment you hit, that place is now moved. Now separate place is there. So virtually you will see the same focal spot, but actual focal spot is moving at very high speed. Okay, something like 10,000, 3,000, 8,000 RPM. Okay, so that we manage the heat. Okay, so that's why you see that the difference between left hand side picture is a stationary anode tube, and the right hand side is called rotating anode tube. So once you have rotation, then you have to have rotation drive, not simple like left hand side. Then you have a stator, rotor, everything comes into the picture, and then from power electron side you need to have the rotation drive. Is it, are you able to connect? So this is how the normally X-ray tube works, depending on. So for very very low power, for a hand extremities and other things, we use the stationary inner tube. But once you go to the full body or lumbar or this kind of things or CT, then this becomes bigger and bigger and bigger, and higher the power, then diameter of the target will be much bigger, so that you get more radius, further bigger. Then CT tube comes, because there you need continuous high X-ray, right? And then you go to the cath lab, where hours together X-ray is produced, because your operation will go for hours together, and we keep seeing that how things are happening. Okay, so then it becomes very challenge, right? So X-ray tubes thermally is very challenging, because all the heats is happening into the vacuum. There is no physical media to take the heat out, so lot of complexity into the thermal comes in X-ray tubes. Okay, so any questions here? Okay, just Dr. Plus, how much time I have more?
Maybe 10 to 15 minutes, sir.
Okay, okay. So I will move. So based on that, so this is how a typical uh, X-ray generator looks like. So it will have the high voltage power supply. It will have the filament power supply. Okay. It will have the rotor drive circuit, which is nothing but if you are aware that rotor drives, it can be simple rotor drives of AC switch with capacitor, or it can be a complicated drive with all the PWM and space vector control. Many types of things is there depending on the system. Okay, and then what happens that sometimes uh, we also do that. We have multiple filament. Okay, so for example, if I need only a small power, I can reduce the focal spot size, so that I will get better imaging. So that is called small filament. But if I need a very large power, I cannot manage even with rotation. So I will increase the focal spot size. So I will get image not as sharper as a small filament, but still I will get image. Okay. So there are many standards in IC for those things, that what kind of filament size you can have. So, but if there are multiple filament, or you can see each filament is correspond to one focal spot. So multifocal. So that control also generator does that, which filament it has to ignite into the tube. Okay, then there are something called grid control, which I will explain you, and AEC is called automatic exposure control. Those kind of things is there. That AEC is something like, suppose if the operator does not know what kVA I have to give, what is the high voltage, and what is the filament current I have to give, Then there are some automation is there, where that we have a automatic exposure chamber where we take that optimal exposure which is coming out of the body, and if that is at the optimal level, we say that this is the voltage and this is the filament current you should apply. Okay, so that is little bit on the automation. Grid is something like that. If you go here, so the moment I am giving anything, actually I am interested into the characteristic X-ray, for example. But the moment, even if I started giving the power supply, nothing goes in the zero time, right? So for example, if I have to give 40,000 volt, it will start. So there is a something called rise time, right? So then it will start having some X-ray of this type, which will get mixed. So which may impact our image quality. Actually, I'm interested in the X-ray of this only, whatever is shown into the peak. So what happens that in grid control, if it is there, that we will block the filament movement till the optimum voltage has come. Okay, so we will wait for the voltage, so some kind of control. Otherwise, if filament is open, so it is kind of filament control. So we put something, a grid, which blocks the electron movement, and nothing but, if you are from electrical engineering, giving a positive voltage very near to the filament. So what will happen, that it will not go to the target, it will just go to the positive voltage which is very near to, because everyone like electron, we like the shortcuts, right? So electron also like the shortcut. So if the positive voltage is nearby, it will just go there, so it will not go to the target. So voltage is building up, but electron is not going, and that's what is called the grid control. So we have grid control, we have the automatic exposure control. This all are the management of the X-ray, but fundamentally it is motor drives, high voltage, and the filament. Okay, and this all are managed by the X-ray generator. Then there are many things is come. This, if you are aware, or otherwise in 1 minute I can tell you. KVP is the, what is actually the peak value of the high voltage. Okay, and then MA is nothing but it is milliampere. So what happens, that the electron movement, whatever goes from the cathode to anode, is also a current, and that is typically into milliamperes. That's why it is called MA. And then how much X-ray will be generated in quantity is called that, it's proportional to that how much MA is flowing between cathode to electrode into the time. So it is called MAS or MA in time. Then focus size, you all, I just explained. Okay, then any contrast load, anything is there. Then AC, fluoroscopic is like multiple uh, picture. It's like a movie, it's a scopic, right? So typically what happens, that one exposure is there, I will get one image. But if you want multiple exposure, then continuous things is there. So there are two types of fluoroscope. Continuous means I keep giving the exposure, and then there are something like, our eye cannot differentiate below 30 above 30 frame per second. So if I take 30 X-ray image in 1 second, it will look like a cinema. Okay, so it is like a moving picture. Typically the cath lab is a moving picture, right? You see that how the contrast is moving and how, where it is going. So that those are called the fluoroscopic mode. So everything is managed by the X-ray generator. Okay, so this is how the first X-ray generator came. When I won't say first, means little bit advancement. First was just a transformer, because X-ray tube, if you understood, only one direction current comes. So even if you give AC across the AC, across the tube, only one direction current will go. But this is the second generation. So it is just a transformer and the rectification. Okay, so you actually have a high voltage transformer, and you just rectify and give across the X-ray tube. Okay, and then there are some switch control auto transformer, like which if you need high voltage, give the higher voltage through the auto transformer. If it is low voltage, so some kind of things, right? And then similar things of filament. But filament, since it is at cathode, there is also called some kind of isolation transformer. So it is like whatever the kV comes between primary and secondary, there is a isolation of that much. And then it is also based on that how much you want to give filament. There is a kind of rheostat, you do that. So this is how it started. And then later everything from the power electronics and this one we started, because this will be like a very big, you can imagine how big it will be if it is a 150,000 kilovolt transformer. It's like kind of half of the room will be filled with that. Okay, if it is a normal 50%. So that's how, but that's how the X-ray generator started, and now it is coming into the 10 kg generator. So a lot of things had happened. This is how the one pulse with just AC was given. So half of the cycle it will go, and this is how the emission will look like. Then full rectifier came, what you saw in the picture. So you get full wave, right? But still you can see that this is how the emission will look like. Then the next third generation came, where we give the 6 pulse or 3 phase, you can say. So you are getting a little bit better with 33% of the ripple. Okay, so a little bit better into that. Then there were 12 pulse inverter also was introduced, something like that. Then high frequency came, and then a full fledged power electronics constant voltage, where we introduced the capacitor. So there are many generation of the this one. Unfortunately, in India you will find still the all types. Okay, depending on that where you are. But that the recent trend is the constant voltage, where we actually do the closed loop control. Till E it was open loop control, means I am giving and something is coming. And the F is that I give now command of 140 kV and I will control the 140 kV, right? Those kind of things. So this is how the evolution of the X-ray generator has been there. So a typical block diagram. So what we do is that if we have to make it small, you all know that frequency is important, right? So if I am isolating on generating a high voltage at 50 hertz, it is very big because magnetic design is at 50 hertz. But what about if I put the 100 kilohertz or 200 kilohertz? Same thing will come down drastically, right? Based on so then that's where the power electronics comes. So this is one of the typical Google image, okay? Because I cannot share you what we do in GE and other things, unfortunately, because those are the trade secrets. So this is typical. So, but you have many stages where you can use power electronics to save the voltage and reduce the size, still get the same result. Okay, for example, one of the technique here is that we still make, in place of fluctuating DC bus, we can use either PFC or buck converter to make a stable DC. And then here you can control the DC itself, and this is a high voltage high frequency inverter, so it is a high frequency AC, and then high frequency AC that your actual transformer becomes very small and you do the same thing. Okay, so but this is one way. There are multiple other ways you can utilize the power electronic circuit and topology. And if you are interested, you can search my name into the patent. Couple of things you will find how you can make it smaller and smaller and smaller to generate the same thing. So you can, here you can see only one transformer is there, but you have many other high voltage circuitry where we generate less AC and then we multiply. Typical is Concroft multiplier, where you can use the multiplier. So in place of giving 150 kV directly, I can have only 10,000 volt and then I can multiply. Okay. So those kind of, any questions up to here before I end?
Hello, sir.
Yeah.
Hello.
Yeah.
I got a quick question. Actually, I'm Tyagesh from Biotechnology Department.
Yeah.
So normally we use this X-ray generators for X-ray crystallography to study the protein structures.
Yeah.
So what I was wondering, like, in terms of the make, how different are these X-ray generators from the one we use it for the medical one?
It's mainly on the kV difference, so as I told you that based on the material, be it metal or some crystal or some body or soft tissue and hard tissue, uh, the characteristic of X-ray is very important, which has penetrating power. Okay, for example, a metallic structure, metal is much more dense than our bone. Okay, so for that we go to 2000 240 kV, 300 kV, 450 kV kind of structure. Okay, generator, we generate very high kV, so that the characteristic of the X-ray is totally different. Whole idea is that based on the imaging technique, once material is finalized, we can find that what is the characteristic of X-ray is required, and in your case it will be a little bit higher kV, I believe. Maybe crystal is around 180 to 200 kV.
Okay, sir. Thank you so much.
Yeah. Okay, so couple of example I just gave. This is one of my patent. You can say that compact X-ray radiation, where this is not the innovation, but for example, you can say that as an engineer, as I told you, I'm engineer. So it's not only the electronic circuit. How do you package it? That itself is there. So this is one of the things called ring multiplier. So you can see that from the high frequency AC, I can either generate here the 150 kV, or I reduce to the something like 5 to 6 kV. So this is very compact. And then it is just diode and capacitor, right? Which multiplies. So every stage is multiplied by 2. Okay. Now, this is not innovation because this is well-known circuit, but how you will package it so that you can manage. So you see that here I put one diode and one capacitor, which is a series of diode and series of capacitor, because you have to stack many diode and many capacitors to get the same thing. And then it is in the form of ring, and the ring is placed around the X-ray tube. Do you see that? And so what happens that it becomes a very compact. Okay, so that this was like around less than 10 kg X-ray generator, which gives you a 4 kilowatt and 100 mass kind of things. So there are a lot of work has happened on the packaging of this one. In this, if you see, this is high voltage transformer, this is the filament isolation transformer. All are this particular things works at 300 kilohertz of the frequency, so that everything is very compact. The capacitor required is very less. The insulation, whatever you need, is that if the right type of insulation is there, that you can reduce the size of the insulator and things like that. So lot of things. So X-ray generator is not only power electronics. It's lot of engineering from all aspects, from material, from the packaging, from the flowing that electrical field all across this one, so this is just a glimpse. I told you that what kind of work I have been doing, and this is publicly in paper, so I could include here. Similarly, one of the PFC of my very earlier career, how we can reduce the total size of power factor unit so that it is compact, and this is one of the my work is on the algorithm, where whole idea is very simple. Normally PFC has a ramp up time. It takes around 40 to 50 millisecond to reach to the maximum current. You do something, a predictive things, so that you know that what power is coming. So it is kind of feed forward control, where you draw the current from t equal to 0 to the max the moment load came. So the moment load is coming, you are giving so that your storage requirement goes down, so that your overall generator becomes small. And if it is smaller, then there are a lot of usage is coming. Okay, so there are many works. I can keep talking this one. So that's what I thought that it is appropriate in this. Any last questions, or anybody has any questions, I will be happy to answer. And also I will ask Dr. Plas to see that if time still permits, we can discuss further.
Yeah, time is there. So time is there. The participants may pose few questions from the Mr. Kumar.
Yeah.
Okay, please ask. Anyone from the audience?
Sir,
Yeah.
yes, sir. Sir, I am a
Yeah.
class for thermal engineering. So
Yeah.
my question is, does any X-ray causes for body harmful? Any side effect?
Yes, X-ray is harmful in one line. Answer is yes. But what happens that it depends on the doses, when say quantity of X-ray. So for example, a normal X-ray, there's no proven thing that it has caused any problem. For example, if you go to the chest X-ray and other things, even in pregnancy, we in emergency uses we allow up to the 7 scan of
Yes.
100 mass. Okay, but if you go in theoretically, does it cause it? Answer is yes, because X-ray finally goes to the body and it enters in your body cells. Okay,
Yes,
and
sir.
if it kills the body cells, no harm. But it stays the energy, soft X-ray. Okay,
Yes.
then it is harmful. So that's why you see that entire this one. The whole idea was that why from the A to F journey has come. Actual imaging, if you can follow my this one, actual imaging need is only on the peak. The rest everything is the soft X-ray. Okay, so if you see that entire research and development has happened to reduce the KVP remains same, but reduce the soft X-rays so that it is less and less harmful. So if you go to the latest generation, there is no soft X-ray, very minimal soft X-ray which comes at the rise and which comes at the fall. Okay, but
Yes,
if
sir.
you so soft X-ray is harmful, but in CT and nuclear medicine, no, it is high. So there can be side effect of cell mutation or something.
Okay, sir. Thank you, sir.
Yeah, yeah.
One
So we
question
can
from
say
my
that,
side. Yeah, please continue.
so we can say that these are all like helping to totally kill that cancer cell and
Yes,
hurting us
yes.
less.
Yeah, if you see the beyond that X-ray is also used to do the radiation therapy.
Yes, sir.
Okay,
Less
where
harmful.
yeah, go ahead.
So you mean that it causes less harm, right?
Uh, Answer is that yes and no. Answer is that whenever those kind of things we take, no, it is against the it's kind of profit loss. So I have cancer anyhow, people are going to die. Okay, so at that time your main aim is to kill the cancerous tumor, but during the killing, although now advanced equipment is coming, they give pointed radiation, but it is going to do some harm, and some secondary radiation, it can get mutated and it can create another cancerous cell. Okay, but at that point, that's why I told it is at that point it is used like that, so that right now you will get relief, and then later side effect will come. But normal X-ray, there's no harm, because normal atmosphere you get much more radiation when you walk outside nowadays through the cosmic things than the X-ray machine.
Okay, okay. Thank you.
Yeah.
Any further questions, participants? Sir, one last question I have from my side.
Yeah.
As you have told in this particular slides, that we are going from alternating to the direct current, this thing,
Yeah.
more of a DC kind. So, is there any efforts are being made in terms of reducing the width of this time pulse? I mean, it's equally important to reduce the width of the pulse also. Apart
Yes,
from
yes. Actually, there is a lot. Actually, if you, unfortunately, I cannot present because those are the company secrets. So,
okay, sir.
but we can now we have developed. You can search the Pierce gun theory on the Google. Okay,
Yeah.
and we have developed a technology where we can modulate the kV in less than 10 seconds. okay, not through the discharge, through the resonance, this one. So if I trigger the resonance here, I can take all energy and store somewhere, and whenever the next pulse is needed, I can force the energy again. So it's like a 10 nanosecond rise time and 10 nanosecond fall time, you know. So it's like a, then you can control the way you want the kV level change or this one through that technology. And if you go to the Pierce gun, no, I can control that electron cloud the way we want. So at the end, you can take this graph the way you want, a separate control of MA and separate control of kilovolt. But those things I cannot present here, so it's a little bit on the trade secret side.
Okay, sir.
Yeah. But there are a lot of efforts is going on in the advanced CT, no, high end CT. We do a lot, because eye is very sensitive, you know. So when we do the scanning, we suppress that X-ray when it comes to the eye. Okay, so that we do only from the likewise, there are many organ which is more sensitive to the X-ray, and if it is not needed, we suppress that X-ray. So we can modulate the X-ray beam now like the way you want. It's like very, very fast.
Okay.
Just to give you a glimpse, G and Philips both are the new system is a 0.2 second gantry, you know, 0.2 second one round. It is like a kind of aircraft machine moving. Okay, 0.2 second rotation, and during that it takes 1000 image in 0.2 second. So which is like you can imagine that one pulse of the X-ray, how short it will be. Okay, because one rotation is 1000 image. Okay, and shorter the time, that means higher power. So we give a lot of power, something like 150 kilowatt, which means that it is like more than 1000 MA, and then very short, very, very short pulses. Okay.
Thank you, sir. Yeah. So yeah, if there are no further questions, then I would like to thank Mr. Kumar. Really, you gave from starting from the very basics of types of machines, and then about the methods to generate those X-ray, and then from the product point of view, how the product is being created. So definitely, you have thrown a lot of light on this topic, and participants who are working in this particular area or in the allied domains can definitely uh, take advantage of this and be in contact with us for any further discussion. So thank you very much, Dr. Kumar, Mr. Kumar. And we all thank you, myself, Dr. Thagesh and Dr. Shibraman. Thank you for joining us.
Yeah.
Hope to see you soon again, sir. Yeah.
Yeah. Thank you very much. Thank you for the opportunity. It was really nice to be connected with you all, and let's be in touch through our normal social media. So I will be glad to be in touch with any of you and discuss further what I can discuss beyond the company's restriction.
Yeah, sure. Yeah.
Thank you. Thank you.
Thank you very much, sir. Thank you very much.
Thank you. Bye bye.
Thank you,
Bye-bye,
sir.
sir.
Thank you.
Thank you, sir.
So, sir.
Uh, so I have one small announcement for the participants.
Just a minute. Let me.
Yeah, sure, sir. Sure, sir. So we have a small announcement for the participants. Actually, today's schedule was from 2:30 to 4:30 for Dr. Gandhi from IIT Delhi. But because of some unavoidable conditions, he won't be able to join at that time. So we have arranged his lecture from 12:30 to I think till 1:30 or maximum quarter to 2. So we request all the participants to please be available at 12:30 only for today. And from tomorrow, as per the schedule. So we request you all to join again at 12:30, and the talk will be by Dr. Gandhi from IIT Delhi on the topics as given in the schedule. So kindly join at 12:30. Is it okay, Dr. Thagesh?
Yeah, Dr. Palash is fine.
Yeah. So please join us at 12:30 in the same link. Thank you, everyone. Thank you. And everyone, if someone has a doubt, they can easily, very nicely, they can pose the questions. Okay. We want this FDP. It's not any kind of some fundraising this thing. Definitely, you all should interact with each other, and at least we all should see each other once face to face, if not by offline, and let us be connected further for 5 days. So you can pose any sort of questions and any query which you have either to me or any of the hosts. Fine, we'll meet at 12:30.
Palash,
Yeah, Thakesh. Yeah,
you can stop the recording now, actually.
yeah. And also the recording will be available to all the participants. So definitely you can have a recording. But I request you to join the sessions. At least the online feel is completely different.
Palash, Dr. Palash.
Yeah, Dr. Shivraman. Yes, sir.
Yeah, Dr. Tapan Kumar Gandhi's session has been preponed to 12:30 now.
12:30. Yes.
Okay. The afternoon, Dr. Tyagesh.
Afternoon session will be like it will be over for today then.
Okay.